All right, so we're looking at rationalizing the denominator. So very first thing we have to do is figure out that the top is the numerator, the bottom is the denominator. We can write that in. I don't know if I'm going to spell them both right. We'll find out. And the bottom is going to be the denominator. There we go. I think I got it. I scribbled so you can't tell if I made a spelling here. But anyways, we got a numerator and denominator. So when they say rationalize denominator, what they're saying is that we don't want a radical or a root on the bottom as the denominator. So how do we do that? Well, we can actually multiply the numerator and denominator by whatever the denominator is. It's the same idea of equivalent fractions. So if I have 2 over 4, well, I can multiply both the top and the bottom by 4, 4 being the denominator. Really doesn't matter what I multiply by, right? And I would get 8 over 16, and these two things are equal, okay? So with that being said, to rationalize something, I need to multiply a root by a root, in fact, by the exact same root. So we have root 6 there, so I'm going to rationalize by multiplying both the top and the bottom by that. Now, before I do that, to make this a little simpler, I'm going to start reducing this fraction. So 15 on top, well, I can kind of break this into prime numbers, but another way to think of it is, well, can I divide something into 15 that also goes into this coefficient 6? So 15 can kind of be broken into like 3 and 5, right? 3 times 5 would be 15. And 6 can be broken into 3 times 2, and then we still have to have that root 6. The reason I did that is so that I can eliminate my 3's. They disappear. So the question now is a little simpler. It's 5 over 2 times root 6. We still need to rationalize. So to rationalize, I take this denominator, 2 times root 6, and I multiply both the top and the bottom by that. So in order to do this, think of these values in the front, those natural numbers, as coefficients. And this, not quite a variable, but something that I can't multiply a natural number into. So instead all I do is 5 times 2. Well, 5 times 2 is 10. Okay? And I still attach that root 6 the way it'd be attached to like something like x. If that was 2x, it'd be just 10x. We just can't do anything with that root right now. Over here, same idea. But I can actually multiply. So I should show you this as, so if this was like 5 times 2x, we would have 10x. On the bottom here, if this was 2x times 2x, you would end up with 4x squared. So those variables, or in this case, no thank you, those variables in this case, this is a root times a root. So first let's deal with the coefficients. 2 times 2 is going to be 4. Root times a root. Well, it's really whatever those roots squared, and a squared gets rid of that radical. So in other words, the easiest way to think of it is
6 times 6.
It's root 6 times root 6, which is actually just the value of 6. Think of it like this.
Oh, it's just like this, the cube.
The square root gets
square.
flipped. So because the square root of 6 is a really hard number to deal with, we don't really write it out. But think of this idea. If I had root 9, well, that's 3 times root 9 is 3, and 3 times 3 is 9. So really, why go through these middle steps? If I know that the root of 9 times the root of 9 is just going to be 9, I don't need to break it down. Same idea here. I'm not going to break down these because the root of 6 is going to be 2 something. It's going to be an infinite number, and I'm never going to be able to calculate that by hand. But because they're the same value, and there's 2 of them, and that's looking for square roots, I know that I can just kind of eliminate the roots and just go with the value underneath.
Okay, yeah.
So now that we have that, 4 times 6 on the bottom, so we have 10 times root 6. 4 times 6 is 24. And then we can reduce our fraction. 10 can be written as 2 times 5. Again, times that root 6 divided by Q. 2 times 12. And those 2's disappear. And we're left with 5 times root 6 over 12, which is a really different number than we kind of started with up there. But now the value on the bottom is a natural number. There's no radical, so this has been rationalized. This is how we rationalize the denominator.